Trees show up everywhere in computer science, but traversing them efficiently, that's the real challenge. Today, we'll look at an algorithm that turns slow climbs into instant jumps. Welcome to Fully Attributed. Suppose you work at a company. You're given a list of employees and their managers, and there's one person at the top, the CEO, who doesn't report to anyone. If you think about it, this structure naturally forms a tree where each employee is a node, their manager is the parent, and the CEO is the root. Now, you need to write a program that, given an employee and a number k, returns their kth level manager, that is, who is k steps above them in the hierarchy. For simplicity, let's assign an employee ID to each person, and we'll show that in our tree. In code, we can represent the tree using a parent array, where each index in the array stores the immediate parent of that node. Now, how do we actually solve this problem? The first idea you might have is pretty simple and intuitive. Since we already know the parent of every node u, we can just keep moving up the chain, setting u equal to parent of u repeated k times. At the end of the loop, we would have the kth ancestor stored in u. Since there are n employees, in the worst case, we might have to go up n nodes. So this approach takes big O of n time for each query and big O of n space to store the parent array. That's fine for small trees, but it's really slow for large trees, and even slower if you have to answer this query multiple times. Can we do better? You might think of precomputing and storing all possible answers. In other words, for every employee, we can store who their nth manager is in a 2D array. But now this table would take big O of n square space. Sure, it will give you instant answers, but it's way too large to store in memory. So for a big company, this might not even be feasible to do so. So what can we do? Well, we combine the best of both ideas. Instead of storing every possible jump, we only store jumps of sizes 1, 2, 4, 8, 16, and so on, the powers of 2. Note that in the code, in order to not leave empty space in the array, we can just store the exponent in the second dimension. That means for each node, we store who is 1 level above, 2 levels above, 4 levels above, and so on, and we can combine these jumps to go to any distance efficiently. How? Let's say you want to find the 5th ancestor of this node. Let's write 5 in binary, which is 1, 0, 1. This means 5 is equal to 1 times 4 plus 0 times 2 plus 1 times 1, or basically 5 is equal to 4 plus 1. So this tells us that we first need to jump 4 levels up and then 1 level up. And this can be done for any jump of size k by just writing it in binary, and since there are only log k bits in k, we'll make at most that many jumps, giving us an algorithm that has a time complexity big O of log n to answer each query. And this is exponentially faster than the linear approach, and this method is called binary lifting. But how do we actually go about constructing this jump table? Let's consider node 14. We can store in the up array its immediate parent by just looking it up in the parent array. Next, to find its grandparent, we can first find the parent of node 14, which we just computed, and then find its parent. Next, to find its 4th ancestor, we can go up 2 levels and then go up 2 levels again. Similarly, for the 8th ancestor, we can go up 4 levels and then go up 4 levels again. This works because 2 to the power I equals 2 to the power I minus 1 plus 2 to the power I minus 1. So, the 2 to the power ith ancestor can be found by stacking 2 to the power I minus 1 jumps. And this is true for every node u, so we get this recurrence relation. So, to summarize, here's how we will build the table in code. We'll first create a 2D array up of dimensions n and log n, since there are at max log n jumps, where up ui stores the 2 to the power ith ancestor of node u. First, we will fill the base case, which is just the immediate parent. Then, for every higher power of 2, we use the relation we derived earlier to fill the table, constructing bigger jumps from smaller jumps. This table only takes up big O of n log n space, and once this table is built in big O of n log n time, we can answer any kth ancestor query in just big O of log n. This is the power of binary lifting. But this idea doesn't stop here. The same algorithm can be used to efficiently find the lowest common ancestor of different nodes and also efficiently solve other distance-related problems in trees. But we'll explore them next time, right here on Fully Attributed. Thanks for watching. If you liked the video, make sure to hit the like button and subscribe, and I'll see you in the next video. Goodbye.